Hello, and welcome to this lecture on duality symmetries in string theory. The title of this lecture could instead have been What is String Theory? What string theory used to be was a perturbation theory. It was a theory of loops of string moving through space-time with interactions governed by a small coupling constant, and the theory was defined as a perturbation theory in this coupling constant. And that was a nice and very successful story. But then if one asks oneself what happens as the coupling constant becomes larger, it's an interesting question which would start telling us about the non-perturbative structure of the theory. And what happened in the mid-90s was it was realized that duality symmetries could provide the key to unlocking this non-perturbative structure. Roughly speaking, we can think about trying to understand the theory at large coupling as a perturbation theory in the inverse of that coupling constant. And that itself might be defined as a perturbation theory of a dual theory whose coupling constant was the inverse of the one first thought of. And this was the beginning of a set of ideas which led to big changes in string theory and into what has become known as the second string revolution. And I think it's fair to say that it's very much changed our view of what string theory is, so much so that it is no longer merely a theory of strings, and it's now and to such an extent then that the name has been changed so that now it's referred to as M theory. And I'm particularly pleased to have a chance to talk about this body of ideas, as it's something which I was heavily involved in my work in the 90s. And the two main papers which will be the basis of what I'm going to talk about are my paper with Paul Townsend from 1994 and Edward Witten's paper from 1995. These laid the foundations, and then there's been a huge amount of work since then. And what I'm going to do is talk about some of the ideas from then, but with the benefit of the modern perspective and the modern understanding as to what's going on. In preparing this lecture, I realized that there's a vast amount of material which goes into this, and to give full justice to it would require a whole lecture series. So what I'm going to do is I'm going to focus on some of the key ideas and provide references for those who want to read further. And some of the details and derivations will be the subject of some of the questions on the example sheet, which will lead you through some of the derivations and some of the arguments, and we'll discuss this in more detail in the follow-up lecture where we discuss the problem sheet. So let me change now to sharing my screen. And then I can start writing on my tablet. Good. So let me start by saying a bit more about what the story of what string theory used to be was like, based on the perturbative structure. And let me start by thinking about, before going on to string theory, let me just make a few comments about the analogous statements for field theory. So in perturbation, the typical way of thinking about this is one starts off with a free theory, a basic set of fields representing the fundamental degrees of freedom. And then one adds interactions with each of which is governed by, given by non-quadratic terms in the Lagrangian, each of which is governed by a coupling constant. So one has in general a set of coupling constants, lambda I, so that one might have interaction. Here's a 3-point interaction, and there'd be a coupling constant which goes along with that. And each interaction would have a separate coupling constant, and then we could develop a theory in terms of a perturbation theory in these coupling constants. And there's a well-known recipe for doing that, giving rise to a set of a representation of interactions in terms of Feynman diagrams. But so let's think about, for example, Yang-Mills, where one has the field strength is a coupling constant time, giving the non-abelian term. So here A takes values in a Lie algebra of the Lie algebra of the Lie group, and then one has an action which is f squared and f mu nu squared, and let's have a factor of a quarter. And here one could see that if one takes g to 0, one gets the free theory, and then adding the terms involving g, one's turning on the interactions. And it's often useful to, and so this gives the picture we were just talking about, but there's another viewpoint where instead we take, we rescale and define A primed equals GA, and then if one defines F primed mu nu equals grad A primed plus A primed commutator A primed, the same index structure as before, but now without the G here, this whole thing is just G times the original F mu nu. So now we've got a field strength where there's no coupling constant appearing in the interaction, and now the action can be written as 1 over 4, 1 over G squared, integral of F prime squared. So now we have the G primed outside the action as an overall factor and no term in the interactions. And then in the functional integral, we can write it as dA primed e to the I 1 over G squared, and there's the usual H bar, then the integral of F prime squared. And here we see that H bar G squared always appear together. There's no other place. The G has been rescaled out of the interactions, and so the coupling constant just appears outside the action, the same place as the H bar does in the functional integral. And so we can absorb H bar into G squared, and this combination is the loop counting parameter, so that at L loops one has a factor of H bar G squared, the number of loops minus 1. So at 0 loops or tree level, we have the 1 over G squared that appears in the action, and an L loop contribution will be of order L minus, a factor of L minus 1. So that if we were to look at an interactions, we might have a tree level interaction plus a 1 loop interaction plus a 2 loop interaction. So we'd get a factor of 1 over G squared overall. We get 1 plus G squared plus G to the 4th, and so on appearing here. And so that gives a standard picture for perturbation theory. I've just talked about the example of Yang-Mills. One could look at similar rescalings for the other fields, and one can rescale so that the coupling constant is outside. And the reason I'm going through this rather elementary point is that there's going to be a rather similar point which comes in string theory, in that there's two different ways of thinking about the interactions. So let's talk about, but a key ingredient here, of course, was starting off with a free theory, and it required us to know what the fundamental degrees of freedom are, and then we'd think of the theory as setting up some interactions for those fields. So now let's turn to theory, string theory. So the basic picture is that we might have, for a closed string, would be a loop of string, which would move through space-time, and as it moved through space-time, it would sweep out a cylinder. So here I'm thinking about time as moving in this direction, and there's the action for this is then given by T times the area swept out by the string. So this two-dimensional surface will have an area, and that's the action, and this T is the tension, and it's sometimes T, which is sometimes written, it's got the dimensions of 1 over a length squared, so it's sometimes written as 1 over a particular length scale, which is defined in this theory, which is the length, the string length. So you could also think of it as defining a mass squared, a string mass, and historically it's given by a parameter known as alpha primed. So this is 1 over 2 pi alpha primed. And there's a fundamental length scale which is introduced into the theory, or a fundamental tension, a fundamental dimensional quantity. And this sets the standard length scale of the string and typically determines the typical size of a string. And in the theories we'll be talking, in the fundamental string theories, this string length is of the order of the Planck length, of the order of the 10 to the minus 33 centimeters. This gives rise to, if one looks at the quantization of this, gives rise to, the excitations of the string give rise to an infinite set of particles with masses m squared in units of the string mass squared, minus 1, 0, 1, 2, and so on. So first of all, there's something with mass squared negative, which is a tachyon, which is bad. It's a signal that this particular theory has got a field with negative mass squared, which is usually interpreted as meaning that there's an instability in the vacuum, and it would and so that would lead to formal problems with the theory. At mass zero, we have some massless fields, which include a graviton, an antisymmetric tensor gauge field, and a dilaton. And here we have an infinite tower of massive fields, which typically, as we increase in mass squared, they typically give rise to fields, some higher spin fields with lots of indices, together with lower spin fields at these higher things. And we can think of it as a two-dimensional field theory. If on the string world sheet we introduce a coordinate sigma around the circle, and a tau describing the proper time of the evolution of the string, then the embedding of this cylinder in space-time is given by space-time coordinates dependent on sigma and tau. And then we can think of these as two-dimensional fields, and the action as giving a two-dimensional, defining a two-dimensional field theory, which is designed so as to extremize the area of the world sheets embedded in space-time. This is the basic bosonic string theory. We can modify this by adding 2D Fermi fields and it could be done. It turns out that this could be done in a consistent way. So first of all, introducing these Fermi fields could be thought of as, roughly speaking, introducing fermion currents moving around the loops of the string. And in looking at the quantum theory defined by the bosonic string or the fermionic string, it turns out that there are very stringent restrictions required from requiring the consistency of the theory. For the bosonic theory, it requires the space-time dimension to be equal to 26. And for the ones with fermions, it turns out that the dimension, it only works for space-time dimension 10. And then the theories which emerge have space-time supersymmetry, rather remarkably. They have no tachyon, so there's no negative mass squared term, so there's none of the instability. So if we look at the spectrum of strings, this term is missing, and we'd start off with massless fields, which include these plus their space-time superpartners, because it's a supersymmetric theory, plus super multiplets of all of the higher massive string modes. And rather remarkably, there are precisely 5 consistent theories which arise in this way, each of which looks different. They've got different kinds of fermions introduced into them, but nonetheless, each of them appears to define a consistent quantum theory, which gives ultraviolet finite amplitudes. And in particular, it has these are quantum theories which include gravity, so it gives each of these gives a candidate for a consistent quantum theory of gravity. Now, one of the problems here is that, so one of the issues which immediately arises is, why are there precisely 5 consistent quantum theories of gravity arising in this way? And that's one of the questions I want to address in this lecture. So another feature is that the massless sector, as I've mentioned, is a supersymmetric theory which includes a set of particles including gravity. So it's a supergravity theory. So what about introducing the interactions? So one can think of it as analogously to the way we talked about interactions with field theory. We can think of having a smooth surface which describes one string. We think of time moving left to right. You have one string breaking up into 2 strings, or reading backwards, 2 strings merging to form one string, and we could introduce a coupling constant G associated with that. We can also think about the analogous statement structure. So in this case, we think of the free string theory together with perturbative interactions. And we can also think of rescaling things so that the G instead counts the number of loops. So this way of looking at things is the thing which arises from some approaches to string theory, such as string field theory. But from the worldsheet approach, which I want to talk about, we go to what's known as the string frame, and we have a natural picture of the string interactions in terms of expansion, in terms of the number of in terms of strings moving through spacetime, so the worldsheet approach. So we can think of it as so if we're looking at a 4-point interaction, we can think of the interaction between four asymptotic string states, as thinking about it as having a worldsheet which joins all of these up together. So the way I've drawn it, we're thinking about two string states in the far past coming together, merging to form one large closed string, and then breaking up to form two more, so that we're getting a process which has got two states in going to two states out. And the picture is that one would choose the asymptotic states, and then one would sum over all possible surfaces which interpolated between those. And there would be a loop expansion for this. We can think of this as this plus having an interaction, having a surface with one hole. So we can think of this as a torus with four handles, four tubes stuck on, and then plus one which was had two holes in it. So here we can think of this as two donuts glued together and then four cylinders glued onto that, and so on. And we can think of this as being, so this would have a factor of 1 over g squared. This would have a factor of g to the 0. And this would have a factor of plus g squared. And in general, we'd have g squared to the genus minus 1, where the genus of the surface is telling you about the number of holes. So this is genus 0, this is genus 1, this is genus 2, and this is telling us about the genus of the basic underlying surface on which these tubes are glued onto. So this is saying that we're gluing four cylinders onto a Riemann surface of genus G. So in this picture, we sum over all surfaces. We get an expansion in G depending on the genus of the surfaces, and as a result, we get a picture for the perturbation theory for the expansion for the scattering amplitudes of string theory, and in each case we get a factor of g squared to we get a power series in g squared, and if g is small, we can think it gives a good perturbation theory. One of the features of superstring theory is that at each genus the amplitudes will each be separately well defined and have good ultraviolet properties. in the worldsheet action, we have the integral over d sigma d tau. We introduce a metric on the worldsheet, and let's have indices alpha and beta running over two variables where alpha equals 0 corresponds to tau and alpha equals 1 corresponds to sigma. So we get grad alpha x mu grad beta x nu, which is the basic action. So with this action on its own, extremizing this will give rise to extremizing the area swept out by the worldsheet. And then there's an extra term and there's a coupling to the space-time metric g mu nu of x. And if the space-time metric is not constant, then this describes a nonlinear action which will have nonlinear dependence on x. And so this is described as called a nonlinear sigma model. And then there could be a coupling to a B field, which we introduced by using an epsilon tensor on the worldsheet, B mu nu grad alpha x mu grad beta x nu. And then there could be a coupling to the scalar field. So this is so looking at the couplings to the massless fields in the action, we've got a massless graviton, a massless B field, and this couples to the scalar curvature of the worldsheet metric H. And let's put in a factor 1 over 4 pi. Now, it turns out that integral of 1 over 4 pi times r root hr d sigma d tau is precisely equal to 2 into 1 minus the genus. So here I'm thinking of having gone to a Euclidean signature on the worldsheet. So h is a positive definite metric. So tau is the Euclidean time, and the integral of the curvature turns out rather remarkably to be a topological quantity, and it gives precisely 1 minus the genus times 2. So this means that if we look at the b to the minus the action, then this has got if we think of the scalar field dilaton as being a constant plus some other pieces, if we look at the constant piece, we get e to the minus integral phi 0 r plus other terms with 1 over 4 pi, and this is equal to e to the minus 2 phi 0 to the 1 minus gamma. So this term is that times the terms which come from the other fields, from the non-constant parts of phi and the other fields in the theory. So, but this action, if we look at the phi 0 dependence, it comes with a factor like this. So we see that if we look at this, so this is precisely the same way in which the g squared appeared. So in fact, we find that at genus gamma, we get a power of g squared to the gamma minus 1 and e to the minus 2 phi 0. Sorry, e to the plus 2 that to the gamma minus 1. So now we see that g and phi 0 always enter in this combination. And so there's a symmetry under which you take g goes to lambda g, and phi 0 goes to phi 0 minus c minus lambda. So you scale g and shift phi 0. So that means that g can be absorbed into phi 0, and we don't need to talk separately about the coupling constant. We, or rather, can think of the strength coupling is associated with the dilaton field, as it's associated with the of e to the phi. So if phi is a constant, we can, or has a well-defined vacuum expectation value in a background with a well-defined expectation value, then we can think of the string coupling constant as being given by the expectation value of e to the phi. And more generally, we can think if we have a varying a background where phi is the dilaton is weak in some areas and strong in others, we can say that there's some regions of the background in which the string is weakly coupled and others where it's strongly coupled. And this is a general feature in string theory, that the coupling constants, and I'll say more about what these are in a moment, all come as vacuum expectation values of scalars. And so that gives us a very nice way of, so in some ways there aren't independent coupling constants, there's rather just scalar fields, and the expectation values determine strengths of coupling. So now we come to the question about that we started with. If we think about strings before 1994, string theory was defined as a perturbation theory and it gave a prescription for calculating the scattering of string states perturbatively in the coupling constant. And it gave a very nice picture, and it turns out there were 5 different distinct perturbation theories, all of which seem to give consistent theories. And so I want to return now to what happens if, as G gets larger, so that the perturbation theory may or may not be valid. So let's think in some generality about both field theories and string theories. First of all, in general, in field theories, the coupling constants will get renormalized, so they will get dependent on energy or temperature. And so as a result, even if you started off with one small value of the coupling constant, as you change the energy or change the temperature, then that value might grow, and so you need to confront what happened at other values. So for example, in QCD, at high energies or high temperatures, it's weakly coupled, but as one reduces the temperature, it becomes more and more strongly coupled, and so the picture one has of it changes, and one's forced to confront the issues of strong coupling. However, some theories, for some theories, the coupling constants are not renormalized. In particular, if supersymmetric theories which are finite, for example, n equals 4 super Yang-Mills, the coupling constant does not get renormalized. So it becomes a parameter which just parameterizes the theory, and we can think about the theory for different values of the parameters. And the same is true in string theory, but as we've just seen, the coupling constants arise as expectation values of fields. And because we want to consider arbitrary field configurations, we're forced to think about what happens if in a configuration where the coupling constants are large. So a big role is in the presentation was played by the free fields, the free field limit, where we take the coupling constant to 0 and we get the fundamental degrees of freedom, at least for the perturbative theory. But as one increases the coupling constant, there's a question about whether the fundamental degrees of freedom remain the same. And for many theories, what happens is that some of the degrees of freedom, some of the particles may become unstable as you turn up the strength of the coupling. And in particular, in string theory, many of the massive string states turn out to be unstable as one turns up the coupling. And so states which are in the perturbative string spectrum for small coupling will not be there for large coupling. And so there's a question about what the right set of fundamental degrees of freedom might be. In general, in theories, then, as you turn up the coupling, there may also be phase transitions, so that you might get a completely different physics and a completely different set of fundamental degrees of freedom. Another related question is whether the theory is actually defined for all values of G of the coupling constant, or whether there's some maximum value of the coupling constant, and what happens as one turns that up. So if the theory is defined for all values of the coupling constant, we can then consider, so suppose theory defined for all values of the coupling constant. As G becomes very large, 1 over G is small, obviously, and you can ask whether we can think, can we analyse as a perturbation theory in a G tilde, which is 1 over G. And rather remarkably, it turns out in a lot of interesting cases, this is possible. And the theory as a perturbation theory in G tilde defines another perturbative theory. And rather strikingly, it can turn out that this dual theory, which is defined as a perturbation theory in G tilde, have nothing to do with the original theory, or look very different. In particular, it can have very different degrees of freedom. This shouldn't be too surprising, because we saw that degrees of freedom in the weakly coupled theory may not extrapolate to stronger values of the coupling. And so this would lead to a dual theory. And so the strongly coupled behavior of the original theory is then described in terms of as a perturbation theory of the dual theory. One of the issues, of course, is that the original theory is only defined for small g, and to try and understand what happens for large g, and to compare it with the perturbation theory in G tilde, is a problem, because the theory is, we don't even know what the theory is defined as for large g. The original theory is defined as for large g, and so we don't even know what the degrees of freedom are, and so it's not obvious how we would compare that. And understanding how one deals with this is one of the topics is the key topic I want to discuss in this lecture. So I'm going to stop this recording of this first part of the lecture here, and then I'm going to continue in part 2 of the lecture to develop these ideas further.